we have done some formal query languages like relational algebra and relational calculus, of which we did tuple relational calculus. Now, based on these relational algebra and relational calculus, a number of commercial languages are also available. So, among these commercial languages, we have the few typical ones in these commercial languages are commercial database languages, one which is well known as the structured query language SQL. This is based on both relational algebra and relational calculus, and uses a combination of relational algebra and relational calculus. We have got QUEL, which is based on tuple relational calculus, we have got QBE or query by example, which is an interesting table driven method table driven language based on domain relational calculus, etc. There are a number of such languages. Some of them are based on pure relational algebra also. Now, these languages are not meant only for expressing queries. They are complete languages in the sense that they allow for data definition. So, they have a DDL. They will give you a data manipulation language or a query processing language. They will also give you mechanisms for expression of integrity constraints. They will give you mechanisms for expression of access rights, authorization, views, etc. So, among these query languages, today we will see the one which is possibly the most popular of these query languages, namely the language SQL. And typically what we will do is we will study query processing using SQL. That is, we are not going to be very much greatly interested in today's lecture into how to define the database and how to express the integrity constraints, etc. Those we will come to later after we understand how we express queries in a relational language, in a relational database using the language SQL. SQL is called structured query language. It originated from a language called SQL, which was originally developed by the group which developed the system R, the very famous first good system for relational databases management. Now, SQL has got a number of features. It has got a data definition language where you can create the tables, define the attributes, and all the structures of all the tables, the relations, the keys, and all these can be expressed using the data definition language. You've got the query language or the interactive data manipulation language. This is the query language, and we shall see this today. You also have the embedded data manipulation language. That is, you have a language corresponding which is quite similar to DML. Given a certain format, you can embed these queries or these SQL statements in standard languages like C, Fortran, Pascal, etc., and compile it. So this is an embedded data manipulation language is also available. You have got the concept of view definitions, that is, you can give different users a different look of the database, that is, you can show portions of the database only to a particular user. You can specify the authorization, who will do what, who is capable of updating what, and who can see how much of the database. You can express integrity constraints. How we will do so we will see later, of which the keys, the functional dependencies and other aspects will come in. And you can finally express the commands or the transactions and control the transactions using SQL as well. It's a complete language, and after we go through what are views, what is authorization, what are integrity constraints and transactions, then we will see how to do them using SQL. But we have already seen query processing languages like relational algebra and relational calculus, and therefore we shall study how to write down queries using SQL. That is what will be the topic of today's lecture. So today's lecture will be query processing using SQL. As usual, we shall pick up our original example where we had the 5 relations: the book relation with accession number, year of publication and title; the user relation with card number, borrower's name and borrower's address; the supplier relation with supplier name, supplier address; the borrow relation with accession number, card number, date of issue; and the sup relation with accession number, supplier name, price and date of supply. So this is the example we will continue with. We will not formally define the language. We shall go through certain examples, and using these examples it will be usually clear as to what we mean by writing queries in SQL. Any query in SQL is of the following type: select A1, A2, A3, A4 up to AN from R1, R2 up to Rm, where P. Now this where is optional. It is not necessary that where should be given. Now this select is different from the normal select operation of relational algebra, so I will explain what this select from and where means. A1, A2 and AN are a set of attributes. These are set of attributes. These are R1, R2, Rm, these are set of relations. And P is a predicate. Which returns true or false. Just like you had predicates in relational algebra and relational calculus, you will have predicates here. These will be relations and these will be set of attributes. Now this, in relational algebra, this expression means R1 cross R2 cross this is the equivalent relational algebra expression for this SQL statement. This expression says R1, R2, Rm there is a Cartesian product done between R1 to Rm. You select out those tuples which satisfy the predicate P and project out the attributes A1 to AN. Therefore, This select is not to be confused with the select operation of relational algebra. This select means select the attributes. It is actually equivalent to the project operation of relational algebra. From these, and here these are to be combined using the Cartesian product operation, and where P is equivalent to the select operator of relational algebra. Now we will see several examples. The first example is select title from book. The equivalent relational algebra expression for this is this means that you will project out all the titles from book. Now SQL also provides you two additional features. By default, you may have a default setting in which only the distinct titles will come out. If you want all the titles to come out in spite of duplicates, all right, then you will write down select all title from book. This will come, all of them will come out including duplicates. Now if your default includes duplicates, then what, if you want only non-duplicate elements to come out, then you will write down select distinct title from book. So this is the simplest query which we can give. Now let us see the one where we use the where clause. In this example, we say select accession number from book where title equal to compiler design. The equivalent query in relational algebra will be book Now suppose we want to have both accession number as well as year of publication, then we will give this. So this will give me the accession number, year of publication of the book whose title is equal to compiler design. Let us go back to the query again. select, the query is select accession number from book where title equal to compiler design minus select accession number from borrow. This is the set difference operator. So this will take out all accession numbers. This also has got all accession numbers, and it is equivalent to the set difference operator in relational algebra. In this particular case, it will find out all the accession numbers of all the books in compiler design which are still not borrowed, that is, which are there in the library. Other than this minus, you also have the union operation and the intersection operation available. So if you had removed this and written intersection, this is also a valid query, but it would possibly not mean much here. What would this mean? This would actually be equivalent to saying select those books which have been borrowed and whose title is compiler design. If I had removed this minus with an intersection, then it would mean select accession number book where title equal to compiler design intersection, select accession number from borrow. This would give us the accession number of all the books which have been borrowed and whose title is compiler design. You can also put in the union operation. The intersection is the set intersection operation, it is not the AND operation. In set it is the intersection operation. AND is an operation which is available for true and false, Boolean expressions. Now let us see how we will do the natural join. Since it provides you only Cartesian product, you have to explicitly do the natural join. Let us see this example. Select card number from book borrow, two relations where book dot accession number equal to borrow dot accession number. This is equivalent to the relational algebra expression book cross borrow select out book dot accession number is equal to borrow dot accession number and project out card number, which in turn, because this is the only common attribute between book and borrow, since accession number is the only common attribute between book and borrow, this is equivalent to so select out card number from book comma borrow such that book dot accession number equal to borrow dot accession number. Now we are in a position to write some queries. Let us take a very simple query. Find out the card number of borrowers who have taken a book titled Compiler Design. That is, users must have borrowed the book and the book must have the title Compiler Design. Now we can, since we are interested only in the card number, we can get it from the borrow and the book relation. We do not need the user relation because the card number is available here. So in our normal situation, it is book, natural join borrow, and we select out title. This selection is different from the select operator of SQL. Title equal to compiler design, and we want the card number. This is the relational algebra expression, and let us see how we will do it in SQL. In SQL, we require the card number from book and borrow. So we will have to write, say, select. What do we want out? We want the card number out. So we want the card number out from what? From book, comma borrow. Now since this does a Cartesian product, we not only have to write where title is equal to compiler design, we also have to write out and book dot accession number is equal to borrow dot accession number, because this does a Cartesian product, and to take out the equivalent of a natural join, we have to make sure that the common attributes are the same. So this is the equivalent SQL expression for this particular problem. Select out the card number from book, comma borrow. Now since card number exists only in borrow, so it's quite fine to do it this way, and where title is compiler design, and this is in equivalent relational algebra. This is the part where we use the selection, and this is the part where we do the projection, and these are the relations. This is not the only way to write out this particular problem. Let us have a look at another one which solves this problem in the same way and uses another construct of SQL. Select card number from borrow where accession number is in. In means an element of. In means, in the set terminology, is an element of. It must be an element of some set. Now that set is formed here. Now where accession number is in, when you say, then this set must return only a set of accession numbers. Accession number is in where? Select accession number from book where title equal to compiler design. Select accession number from book where title equal to compiler design. So in this part of the query, it returns the accession number of all books whose title is compiler design. And this part of the query selects out those card numbers from borrow such that the accession number must be in this set. So based on this, we can write out this query.
So in this case, if accession number is same in both sides. Maybe we have to specify one very same thing, like borrow dot accession number for.
No, here there is, when I write down accession number, the scope of this accession number is in this borrow relation only. And when I write down this accession number from book, the scope is here. Therefore, for this accession number, you don't have to write down book.accession number. Only whenever there is a confusion. For example, if I had written down book, comma, borrow and accession number, then I would have the confusion of which accession number to take. There I would have to specify. Otherwise, the scope rules, this query is in sense bracketed here, therefore this accession number will be related to this book and this accession number will be related to this card number. This query can be written in other ways as well. I will not discuss all the ways to write down this query, but using the union, intersection and minus operations, you can also write down this query in a slightly different way. So a query can be written out in many ways, and this is one interesting construct which is available, the set element construct. You also have the set subset construct as well. We will see that later on, but you have the set element construct which can be used to write down several interesting queries. The next example which we will try to solve is, find out the name and address of those borrowers who have issued a book on 15/8/94. We want the name and address, so we need the user relation, and the date of issue will be from the borrow relation, so user and borrow is sufficient to solve our problem. And we'll have to do a natural join of user and borrow through card number and get the name and address whose date of issue is. It's a simple problem. So a direct solution to this problem would be select B name, B address, from user, comma, borrow, where user dot card number equal to borrow dot card number and date of issue is equal to, it is a simple query, select borrower name address from user and borrow, where user card number equal to this and date of issue is equal to this. We can use some other ideas of variables to reduce, to prevent us from repeatedly writing out this borrower dot card number equal to borrow dot card number and user dot card number. And using these variables, we can make the queries a bit simpler. That is, we can replace these by variables. That is, the same query can be written out in the following way. select, I put distinct, anyway you need not, borrower name and address from user u. User, the name user will now have the variable u, borrow will have the tuple variable t, where similar to rename or a variable, use of a variable, where u dot card number is equal to t dot card number and date of issue is 15/8/94. So we have just renamed this u and t, and we are using these names now for our query.
Distinct was not required in the last.
I'll just put in distinct, in most cases, in some, why we use distinct. In some of them by default, it is select all. The default usually is select all. And therefore, if you want only the set of distinct names and addresses to come out. Now, if a person has two addresses, then two will come out even in distinct. Same name and two addresses. If there are, for a person, if there is one name with two addresses, then two will come out here, even in distinct. But in many cases, the default is all. There you will have to explicitly write distinct. Then the question is, what is the use of having all? That we will come to later on, where we require to count the number of tuples which come up. We need to add the tuples which come up. We need to find averages and all that. That time we will require the all to be more explicit. Otherwise, all is not very useful directly if we are just answering pure queries.
The variables u and t, is it only for this or it will be continued for next?
The variables u and t will be within the scope of this whole expression. Okay. Now we will see examples where it may go, where, see, suppose you have got a query like this. The question is regarding the scope of variables u and t. The scope of u and t is the same as the scope of user and borrow. Say select x from y and say, let us put it as y, where? Now here if I have another select p from q, where? Now this y still goes into the scope because it is in the part of the where. So now you can write y dot something is equal to q dot something. That is allowed. It should be within the scope of this select statement. The name y, wherever y is allowed, there the same scope will apply for this variable y. The next problem, which was a typical problem of Cartesian product on the same set which required renaming, and we solved this problem both in relational algebra as well as relational calculus. Find out the names of all borrowers who have the same address as Vijay. This will require that on the user relation, the name and address are available on the user relation, and we have to do a Cartesian product on the user relation, rename at least one of them. That is what we did in relational algebra. We renamed one of them. So if you use that idea directly, then you will have select. What we will select out? Somebody's name. From user and user. So the use of the variable and the renaming variable is absolutely essential here. User T, comma user S. And suppose we take out T dot B name, then we will have to have where S dot B name is equal to Vijay, and to get the natural join, T dot B address. It is not the natural join, it is just the Cartesian product, but we are just taking out those places where the address is common. So the query finally becomes select T dot B name from user T and user S, where S dot B name is equal to Vijay and T dot B address is equal to S dot B address. We have renamed one user as T, the other user as S. We have done those places where the addresses are same in the Cartesian product, and where one of the names is Vijay, then we have selected out the other name. Let us see what this query means. It's an interesting query. Select T accession number, comma T dot S name from sub T sub S, where T dot price is greater than S dot price and S dot S name is equal to Narosa. Let us see what the sub relation is. The sub relation has got accession number, S name, price and date of supply. Now we are doing T accession number, T S name from sub T sub S. So anyway we are doing sub, we rename it as T, cross, we rename it as S. This is the first thing that we do. And then we select out where S dot S name equal to Narosa and we select out where S dot price is less than T dot price and we project out T dot accession number and T dot S name. So we've done a Cartesian product between these two subs and we selected out the place where S dot S name is equal to Narosa. That's fine. So one of the suppliers must be Narosa and S dot price must be less than T dot price. This is quite interesting. So Narosa must be less than somebody. That is, there must be somebody whose price, who has supplied a book whose price is greater than that supplied by Narosa. Now it is not greater than all the books supplied by Narosa. Even in one place where S dot S name is Narosa and this price is less than T dot price, that person's name will come out. So this query is equivalent to saying that select out the name and address of those persons who have supplied even one book whose price is more than the least price of Narosa, least price of a book supplied by Narosa. I repeat, find out the name and accession number, supplier name and accession number of those books which cost more than the price of at least one book supplied by Narosa. If there is one book which is supplied by Narosa whose price is less than T dot price in the Cartesian product of these two, then that name will be taken out and accession number of that book will be taken out. Now if there is at least one book whose price is less than the price, or whose one book by say a supplier called Allied has supplied one book whose price is greater than the price of some, even at least one book supplied by Narosa, then Allied's name will come out. So that means it is equivalent to saying that all those who have supplied even one book whose cost is more than the least price cost of a book supplied by Narosa will have to come out. Now even Narosa's name may come out, because if Narosa has supplied two books, then the book which has got more price than the other book will come out. Suppose there are 20 books in the library, alright, and Narosa has supplied 5 books, then 4 of Narosa's names will come out if all the 4 prices are distinct. If all the 4 prices are equal, no name of Narosa will come out, because this is greater than, not greater than, equal to. So suppose in the simple case that all prices are distinct and Narosa has supplied 5 books, then 4 of Narosa's names will come out, and the accession number and supplier name of all books which cost more than the least cost price of Narosa's book will come out. This is the meaning of this query. But SQL allows us to write out these queries in a slightly more simplified and more logically appealing and easier to conceptualize fashion as well. We shall see that a bit later.